So we started with the discussion of process in the last lecture, and then we started with the two-state model for the process, two-state process model, and we derive up to this point, five-state process model, and we discuss all these states: running, ready, blocked or waiting, new state and exit state. And then we also discuss the possible process state transitions and the reasons for that. This is the single block queue. So basically this is representation of that five state diagram using single queue. I mean only one ready queue and one block queue. And then we also discuss that instead of one block queue, we can have multiple block queue based on the events. And then we stop at this point. So let us continue from this. Now suspended process. So if you remember this last one, this particular point, right? In this we have five states, and the block is a state. It represents those processes which are waiting for some IO events or some other events. So now what we are going to see is another concept called suspended processes. So usually processor is faster than IO. So all processes could be waiting for IO. Now just think about this, that whatever processes you have in the system, as the processor is very fast when you compare it with the IO, and if some of the processes are right now waiting for IO, it may happen that all processes which are there in your system at one point, they all are waiting for some IO, and there is no more process which can be executed by the processor, because IO are very slow, right? So it takes more time compared to execution of the process by processor, and processor are very fast when you compare it with the IO process. Compare it with the IO. So in this case, what is the problem? When all the processes are waiting, they are in the block state. So what can be the problem here? So definitely a processor could be idle most of the time, because most of the all the processes, they are spending their most of the time in waiting for some IO, and at that time processor is not being utilized and it is idle. So what can be done in this case? So you can swap these processes to disk to free up more memory and use processor on more processes. Now this makes some sense, because most of the all the processes that you have right now in your system, they are blocked, and processor does not have any process to execute. So what we can do, definitely what we should do, we should swap some of the processes which are blocked from main memory to the disk memory, secondary memory, and let allow some of the new processes to come inside the system and let them execute. So this is the simplest solution. So block state becomes, now in this case, block state becomes suspend state when swapped to disk. So the processes which are blocked, when you put them on the secondary memory, you swap it to the secondary memory. Now this kind of processes which were blocked and now they are put on the secondary memory, they are called suspended processes. So when all of the processes in main memory are in the block state, the OS can suspend one process by putting it in the suspend state and transferring it to the disk. Not necessarily one, it can be one or more than one, depending on the requirement of the memory for the new process. So the space that is freed in main memory can then be used to bring in another process. Okay, so does this make sense to you, what we are doing here? Okay. So now our five-state process model gets converted into six-state process model. You can see that all five states are there, right? And one more state is added, that is suspend state. And you can see the transition from block, it can go to suspend, and from suspend, it can come back to ready. Now, if you see this, when it goes out, we put it, when we put this block process on the secondary memory, it goes from block to suspend state. But when we bring that suspended process back in the system, it comes directly in ready state. Okay. So what do you understand by this? Can anyone answer? What do we understand by this transitions? I would like you to answer this question. Anyone? See, if it is about IO process, IO devices for which you are waiting, normally they are the block processes. Of course, when some block process goes to the suspend state, and when you bring it back, you directly bring it back to the ready. And you are saying that, okay, that you assume that the event on which that process was blocked, it has occurred. And that's why you activate directly into the ready state. Is that so? Is that your answer? But do you know whether it is whether that event on which it was waiting has happened or not? See, so there are two choices to bringing the process in main memory on place of suspended process, right? Okay, before we discuss this transition, there is one more point to be discussed. So let's discuss that. So two choices to bringing the process in main memory on place of suspended. Now you have suspended some process and you means OS wants to bring some new process into the system. So there are two choices. Either you admit that process as a new process, either you admit the new process, okay, or you can bring in a previously suspended process now. See, when I suspend some of the processes, so definitely there is some memory which becomes free so that some other process can be bring in. Now, there are two choices with the OS. Either it can allow new process to get admitted into the system, or some past suspended process, some previously suspended process, it can bring that back into the system. So there are two choices. Okay, this is a typo. No point in bringing the suspended process as it is a block process and cannot ready for execution. First of all, the processes which are there in suspended state, they are basically block processes. So there is no point to bring this block process back into the system, because ultimately why we are putting any process into the suspended state, so that there can be enough memory to bring in some new process which can execute, which can run, and which can execute. If we get any suspended process back into the system, there is no point, because ultimately that is going to wait and it is not going to utilize the processor. So there is no point in bringing the suspended process as it is a block process and not ready for execution. Okay, but as someone just answered that IO devices are now available, so that is one possibility. That is one possibility, that when process it is lying in the suspended state, when it is lying on the secondary memory, meanwhile it was resting there, the event on which it was waiting, that event has happened. So that is the possibility. So now better idea is to expand this state, or you can say divide the single suspend state and replace it by the two different states, that is block suspend and ready suspend. So expand suspend state into two states. Block suspend, it represents the processes which is in the secondary memory and awaiting on some event, whereas ready suspend is the process in secondary memory but is available for execution as soon as it is loaded into the main memory. It means previously it was in block suspend, but now some event on which it was waiting, it has happened, so it will move to the ready suspend state. And it means if you bring back any process from this ready suspend state into the system, it is ready to run. It is ready to run. Are you getting this idea? The expansion of suspend state into two states? Yes. Okay. So now you can see our six-state process model. It is now replaced by the 7-state. Okay. And here the dashed line in the figure indicate possible but not necessary transitions. So this dashed lines, they represent some possible transition but not necessary. Okay. So some of the transitions we have already discussed, like ready to running, running to ready, running to exit. new to ready, we have discussed new to ready, but now we have two states where new process can be admitted either into the ready suspend. Can you hear me?
Yes, sir.
Yeah, there is a power cut, so it got disconnected. Give me a minute. Is my screen visible?
Yes, sir.
So we were discussing about this 7-state process model, and you can see that previously in 5-state model we saw that new process, the newly created process, it gets directly into the ready state. But now we have two options: either newly created process you can put it directly in ready state, or you can put in ready suspend in case of scarcity of the memory. If you don't have enough memory, you can put it in ready suspend also. So there are few new states which we need to discuss. Okay, so let us discuss those new transitions which we haven't seen before. One is block to block suspend. This is a simple state. Okay, the process which is blocked, and you require, OS requires some more memory so that new process can be admitted and processor can be utilized. This block process can be moved to the secondary memory, and that will become the block suspend. Okay, so this suspend state, so we are discussing this suspend state, block to block suspend. Then there is block suspend to ready suspend. Now you tell me when this will happen. When this block process moves from block suspend to ready suspend, we have already discussed, but I want you to answer now this. Yes, so when the event on which that block process was waiting, if that event occurs, this block suspended process will move to ready suspended state. But remember one thing, these two states, ready suspend or block suspend, ultimately the processes which are in these two states, they are on the secondary memory, and all other states, they represent processes which are in the main memory. Okay, so these are the two states where processes are in the secondary memory. Then you have state from ready suspend to ready. Again, it is activated. So this is simple state transition. When there is a chance for OS to bring some more processes into the system, either it allows newly created process, or it allows some ready suspended process to bring into the system. Fine. And now this is important thing. You can see that there are two possibilities for newly created process. Either it can be admitted in ready suspend queue, or it can be admitted directly in ready. So just to understand this point, let us see this way. If newly created process, there is not enough space right now in the main memory, that newly created process will remain there in the secondary memory in ready suspend. Okay, and whenever there will be time, there will be some memory, free memory, it will be bring back into the main memory from ready suspend to ready. Okay, so that is normally how it works, but it is not necessary that it works only this way. whenever, let's say, your system is just booted and processes have just started to be executed, at that time you have enough memory, you have enough primary memory or RAM. In that case, not necessary that newly created process will move here, it will directly move to the ready state. That is possible. So it all depends how much memory is available and what is the scenario. Accordingly, OS will take decision. So this is another new state. One more state. Now you can see something, that running process is not moving to ready. It can also move back to ready suspend. Now this is interesting. Normally running process, okay, when process is switched, when processor is taken back from any executing process, what are the possible scenarios? If any process is running, when it will move to some any other state, normally you can see it can move to three different states, either exit, block, or ready. Forget about this ready suspend right now. So in which case running process will move to exit state? When process is normally completed, finished, right? When it will move to block state? When there is some event on which process is waiting, right? And when it will move to ready state? No, not event. Event occurs, then it will move to block state. Over time or time over? So basically the time which is allocated to this running process, right? The time slot which is given to this running process, that time is over now. So in that case, that running process need to stop for that moment. It has to pause and it will move back to ready state and it will wait for its next turn. It will wait for its next turn. Okay, so in that case, it will move from running to ready. But there is one more state now. Directly, it will be suspended. It is not moving to ready state. Let's say the time slot which is allotted to this running process, it is over. So normally in that case, it moves to ready state. But it is also possible that it will directly move from running to ready suspend, and it depends on the OS design. If OS thinks that it has more priority processes there in the queue, then it can directly move this running process to ready suspend rather than ready, so that there can be enough memory, there can be enough free memory for the higher priority processes to run. Okay, so that is one possibility. So basically these are the states, new transitions that we have discussed. And then there is one more, any to exit. That is also possible, though it is not shown in the diagram. It is not shown here in the diagram, but it is always possible that from any state, from any of the state, process can directly move to exit on different reasons, because of different reasons. Okay, so that is what we discussed. Someone has asked whether ready suspend will be in secondary or main memory. Now you need to answer me. We have already discussed secondary memory. Suspend means secondary memory. The process which is suspended, it is in secondary memory, whether it is ready suspend or block suspend. Is that clear? And there is one transition, possible transition from any to exit, which is not even shown here, but that is also possible. It is possible because of different reasons. One possible reason is, let's say your process is in any of this state, block state or block suspend or ready or wherever. If OS thinks that this process is occupying space and it is not allowing other higher priority processes, so it may simply trace that process. It will simply exit that process, right? It will kill that process. OS can do that. That is one possible reason. Okay, from any state, process can be killed by the OS for reason. What is the reason for that? To free some memory. That is one reason. Another possibility, in some OSs, if parent process exits when it is finishing, whatever children it has created, automatically they will be killed. So it is possible that your parent process right now it is running and some of its children are there in ready state or block state, wherever, but that parent process now it is exiting because it is completed. So in some OS, it is designed that way, that if parent process exits, all children will be terminated. So in that case, the children processes which are there in either ready state or block state, they can be directly killed and they will move to the exit state. So this is another possible reason. One is to free memory. Another is parent may kill some of the children's parent when it is exiting. It will, in that case, OS will kill all the children. So that is another thing. Third possibility, that if some process which is a let's say some process which is running and there is some fatal error which is affecting some other processes also. In that case, that executing process, when it exit, OS will make sure that other connected processes will also exit. So again, these are some design issues that we are discussing. These are some designs that we are discussing. Not necessarily that this is how every OS is designed. Again, I am repeating myself that we are discussing very general OS designs, right? These are some possible designs that you can have in different OSs. So all this design, not necessary that it is there in single OS, right? Depending on the OS implementation, this design vary. But these are some general design points that we are discussing. So, okay, there is one question. Process will go from block suspend to block. Yes, I think we forgot that, right? This is also interesting point. Now, does this make any sense? Thank you for bringing this in my notice. This is very interesting state. What is the point to bring already block suspend process back into the block state? Normally, when we move any process to suspend state, when we want some free memory, when OS wants some free memory. So what is the point to bring this already blocked suspend process in block state? Because it is anyway not going to utilize processor because it is blocked. So this is possible design when OS thinks that the block suspend process of some higher priority is waiting for those events which is about to happen in very near future. If OS thinks that way, if OS has all the reasons to think that way, that the process, block suspend process, which was waiting on some event, that event is going to happen in near future and it is very high priority process. So rather than waiting for right now, let me bring it back in block state, and as the event on which it is waiting, it is going to happen very soon. So it will become ready immediately after that. So if OS has this idea about this process, then it will bring this block suspend process to block state. So that is one possible reason. Does this make sense? Okay. Now, what are the characteristics of the suspended processes? Okay, so let us go through these few points regarding this suspended process. The process is not immediately available for execution. First of all, the suspended process is not immediately available for execution. First of all, why? Because it is in the secondary memory. The process may or may not be waiting on an event. Okay, if it is waiting for the event, this block condition is independent of this suspend condition, and occurrence of the blocking event does not enable the process to be executed immediately. Now what it says, the reason why this process is blocked and the reason why this process is suspended, they are totally two different reasons. Not because process is blocked that it will be suspended. No, it is not like that. What is the reason behind process to get blocked? What are the possible reasons behind processes to get blocked? No, time over, we can't say time over because it is going in ready state. If it is time over, it is waiting for event, simple. Waiting for any type of event, IO event or any other event, right? So if it is waiting for some event, it may be blocked. So that is the reason for process to get blocked. But what is the reason for process to go into the suspend state? Lack of space. Most of the time it is lack of space, right? So now what it says, the process may or may not be waiting on event. Okay. Why? Because suspended process, if it is waiting on event, it is in this state. If it is not waiting on event or event on which it was waiting, if it has happened, then it is in the ready suspend state. So in suspend state, process may be waiting on event or it may not be waiting on event. But if it is waiting on event, it means if it is in the block suspend state, okay, this block condition is independent of the suspend condition. And occurrence of the blocking event does not enable the process to be executed immediately. So what it says, on the event which this block suspend process is waiting, okay, if that event occurs, it does not mean that this process is now immediately get executed or it is ready to execute, right? Because from here first it will move to ready suspend, and when OS will have enough space and it has enough reason to bring in this ready suspend process in the system, then only it will bring it back into the ready state and then it will be ready to execute. Okay, so these are characteristics of suspended process. The process was placed in a suspended state by an agent. Okay, someone puts this process in the suspended state, and that someone is the agent. And who can it be? Either the process itself or a parent process or the OS, for the purpose of preventing its execution. Sometimes process itself can put it into the suspended state. This is interesting. Some processes which need to execute, periodically, let's say, to check the performance or to analyze something. So there are some processes which are called monitor processes or accounting processes, which just need to do some accounting or just need to analyze something. It need to take the screenshot of the resource utilization. So those processes who are running periodically, fixed time, after every 5 minutes, suppose. So those process, when it is completed, it will put itself into the suspend state. Okay, it is possible because it knows that I need not to run for next 5 minutes, so it will put it itself into the suspended. Or sometime parent process, if parent process thinks that this one of its children has misbehaved or it has to be analyzed properly because it has thrown some error or exception or something like that, in that case parent process just put it into the suspended state and work on it. And sometimes OS, mainly for memory reasons. And the process may not be removed from the state until the agent explicitly orders the removal. Okay, so whichever processes are put into the suspended state, they cannot be removed from that suspended state until the agent, and most of the time this agent who removes the process from suspended state and put it into the system in the main memory, most of the time that agent is OS. Most of the time that agent is OS. Okay, so are you getting this characteristics of suspend process? Now, what are the possible reasons for process suspension? One is swapping. The OS needs to release sufficient main memory to bring in a process that is ready to execute. So that is one main reason, swapping. Other OS reason, like OS suspects process of causing a problem. If OS suspects that this process is creating some problem in the system, it may suspend that process. Interactive user request. For example, debugging or in connection with the use of a resource. Okay, if user request some debugging, okay, in that case OS may put that process in the suspend state and then it will be analyzed. Timing, that is another reason. So process may be executed periodically. I just gave this example, right? Accounting or system monitoring processes. So if it needs to execute only for every 5 minutes periodically, so in that case, simply it will put into the suspended state after it gets executed. And after 5 minutes, again, it will be bring back into the system and it will execute. So that is one reason, timing. Parent process request. We have also discussed this. A parent process may wish to suspend execution of descendant to examine or modify the suspended process or to coordinate the activity of various descendants. So these are all different reasons why process gets suspended. Why process gets suspended. But suspended process means it is lying in the secondary memory and no more in the main memory. Is that clear up to this point? So this is all about process states. We started with 2 states, then we used 3 states, then 5, then 6, and finally 7 states. So we finished at the 7 states, and that is a very general design. 7 states means very general design. In fact, in this chapter itself, we'll be discussing Unix process states. There are 9 states, and we will be discussing that. Okay, someone has asked, block is passed to suspended via interrupt. Not necessarily. I mean, it is like, when OS gets its time to execute, at that time it will decide this, that okay, there is some free memory required, so let me put some of the block processes into suspend state. So it depends on the OS design, okay, how it is implemented. Interrupt, possible reason that because let's say some process requires more memory, and there is some interrupt occurs that enough memory is not available. Maybe OS is handling that interrupt so that it can free some main memory by putting this block process in the suspended state. So that is also possible reason. I mean, also possible implementation. So the implementation, if we talk about implementation, it varies from OS to OS. Does this make sense, Pujal? Okay. Any question up to this point? So basically till now we have discussed process states. After this, we are going to discuss data structures which are required to manage a process. That is our next topic. And while I am discussing the whole chapter, few of the concepts are occurring again and again. So don't get confused, but definitely that will help you to digest that concept. You may think that, okay, this concept is coming again and again, but it is not that way. Normally, the way this chapter is written by the author, what he has done, first he has touched the idea of the concept. I mean, whatever the topic is there, and then he is going in the detail of that. So definitely you may think that some topic is coming again and again, but it is not that way. We are actually digging in. Okay. So this is process states. Now we will be discussing data structures used to manage processes. That is our next topic. Okay. Before we start with directly data structures, let us understand the relation between processes and resources. Actually, if you remember, in the very initial stage, we discussed that OS can be seen as a resource manager. I hope you remember that. OS can be visualized, or OS can be thought of as resource manager, because it has to manage resources. What kind of resources? It can be IO resources, it can be files, it can be processor itself is a resource. And when it comes to process, okay, process, when it is executing, it is owning some resources, or it has occupied some resources so that it can complete its job. For example, here you can see P1, P2 up to Pn. These are the processes, and these are some resources, right? Computer resources. It can be processor, it can be different IO devices, it can be main memory. Main memory is also a resource. Okay. Now what you see here is P1 currently it has occupied 4 resources. Processor, because it is executing. So in that case, we can say that when P1 has occupied processor, it means P1 is running. It is in the running state. It has occupied 2 IO devices, and it has occupied main memory. Now, can anyone answer this question? Why process occupies main memory? What is the point? Or what do you understand by that? What do you understand that process occupies main memory as a resource? Yes, can anyone explain this? For example, process required IO, let's say some printer, some keyboard, or something like that, right? So it has occupied these resources, and it is working with those resources, because when it is executing, it is working with those resources. How about main memory? Why main memory can be considered as computer resource? Anyone? Because when we say process, what is process? We have already talked about it little bit. What is process? What is manifestation of process? I can say that this PPT that I am executing right now, I am showing you, it is running some program. So it is a program in execution, correct? It is a program in execution. Okay. But when program in execution and you call it a process, but is that the only program? Process is just a program which is executing. What else it is? We have already discussed this. You should remember. It is nothing but the program in execution, the program plus the data on which that program is working or executing. And third is some attributes, some states, right? So all this combinedly create a process. And where you put all this data, where you store all these attributes, where you store data, where you store program, main memory. So that is why any process which needs to execute, first of all, it must be in main memory. That is why main memory can be considered as a resource. And this dotted line means that process has requested that particular resource, but it is not given because there is no enough resource to provide it. For an example, P2 is asking for this IO, and this IO is currently occupied by P1, so it cannot be given to P2. So as P2 is waiting on this IO, it cannot process further. So you can see processor is not with P2, it is waiting, it is a block process. Similarly, PN. Now this is interesting. PN. Okay. This process, it is waiting for main memory. So what does it means? What does it means? If process is waiting for main memory, what do you understand by that? It is waiting for main memory. It is not given main memory. So what is the state of this process? No, not new process, because new process has some different, we'll see that. Basically, it is a suspended process. You can say it's a suspended process, not block. Block process is this P2, which is in main memory. Okay, again, fine. You can see that P2 is already having main memory. That is what it is shown here. That is what it is shown here. And PN, it does not have any other resource, but it is waiting for main memory. It means it is waiting for itself to get into the main memory. Okay, and that is why it is considered as a suspended process. Now the point is, here we are not putting like secondary memory. This is not secondary memory. This is virtual memory. Do you know the meaning of virtual memory? Do you have any idea what is virtual memory? Anyone? Any idea regarding virtual memory? Okay. Virtual memory is nothing but it is the extension of main memory on the secondary memory. So there is some space in your hard disk which is considered as part of main memory, but it is not. And that is called virtual memory. It behaves like it is the extension of the main memory, but still it is not main memory. It is still on the secondary memory, but it is a special memory where, I mean, that virtual memory contains special things like processes which are swapped out. They are normally on the secondary memory. And virtual memory is definitely a part of hard disk, but it is considered as the extension of main memory, but not the main memory. So definitely we will discuss what is virtual memory further when we discuss the memory management. So you can see that processes and resources relationship here, right? Now let's go to the data structures that are required to manage a process. So OS control structure we are going to discuss. For the OS to manage processes and resources, right? So because processes are directly working with resources, and OS as a resource manager, it has to manage these relations also. OS has to, while it is managing resources, basically it has to manage this relationship between process and resources. So for the OS to manage processes and resources, it must have information about the current status of each process and resource both. So now OS has to have information regarding all the processes and all the resources which are there in the system. And to manage, to maintain that information, some data structure, some table is required. So tables are constructed for each entity the operating system manages. So now we are going towards the data structure. So OS needs to manage some tables for each and every entity. So this is again very simplified design. This is very simplified design. It is not always like this simple. It is very complex actually. There are so many cross references from one table to other, especially processes references are there almost in all the tables. So you can see here that these are the four things, four entities which are managed by OS: memory, devices, files, and processes. Okay, and you can see that for each type of entity there is one table. For memory there is memory tables, for devices there is IO tables, for files there is file tables, and for processes there are process table. There is a process table. Okay, so again this is very simplified design. When you go into the actual design of some actual OS, you may get it very complex. Again, we are trying to touch the design of Unix system. At that time you may find it a bit complex. So the point here is OS needs to manage some tables for each entity that it is managing. So what is memory tables? What it is all about? So memory tables are used to keep track of both main and secondary memory. These memory tables, they are used to keep track of both main and secondary memory. Both memories are managed by this in this managed table. Both memories information are maintained in this memory tables. It must include some information like allocation of main memory to processes, which part of main memory is allocated to which process, that it has to maintain. Allocation of secondary memory to processes, because as I told you, there is some extension of main memory on secondary memory, which is called virtual memory. So it has to manage that virtual memory also. Protection attributes for access to shared memory regions. There are some memory regions in the main memory which are shared by different processes. As I already given you, I have already given you one example, shared memory example. A same program, let's say you are using MS Word, and there are multiple MS Word files you have opened. So they are different processes, but they are using the same code. So in that case, it's a shared memory. So it is required to assign some attributes to this shared memory so that it cannot be corrupted by some other process. So protection attributes for access to shared memory regions, that is there. Information needed to manage virtual memory. We'll see what is virtual memory and how it works. So these are some information that memory tables need to have so that OS can manage all of them. Some IO tables are information, so used by the OS to manage the IO devices and channels of the computer. Channels mean bus, right? The OS needs to know, what OS needs to know to manage IOs? Whether the IO device is available or assigned. What is the status? It is available or it is already assigned to some process. The status of IO operation. If it is assigned, what is the status of that IO operation? Is it reading? Is it writing? What it is doing? The location in main memory being used as the source or destination of the IO transfer. Let's say you are transferring some file from, you are opening some file from secondary memory and you are putting in the main memory. So basically you are reading some file and you are putting into the main memory. So you need to know, OS needs to know what is the location in main memory which is being used as the source or destination of the IO transfer. If you are transferring, if you are opening some file, it will be brought into the main memory from secondary memory. So you are reading it. So in main memory, at which part, at which location you are reading it, that OS needs to know. If you are writing that file, okay, so it becomes source. So it also needs to know from which portion of the main memory you are writing content to the hard disk. So basically, whatever IO does, that all information needs to be managed by OS, and for that IO tables are used. File tables, These tables provide information about existence of files, whether file exists or not, or where it exists, location of the secondary memory. So on secondary memory, where this file is, that is there, current status, whether this file is opened or not, whether this file is being read or written, what is the status, other attributes, right? Other attributes like what is the permission of this file, who can access it, whether it is readable or writable or both. So this kind of information for each file needs to be managed, and most of the time it is managed with by the file system. Okay, file management system most of the time, but in some primitive OSs it was done directly by OS, but nowadays in most of the OSs file management systems are there and they do all this stuff, but it is also part of OS. File management system is also part of OS, but it is a separate module now. So do you know any file management system that you might have heard about? Have you heard about any file management systems? You must have heard about. Yes. Are you guys there? Are you sleeping? What's the case? Yes, FAT32, NTFS, they all are file management systems, and these are the Windows file management system. Anyone who knows any Linux file management system? ext3, ext4, have you heard about this? Okay, so in Linux these are the file system: ext3, ext4. Ext4, I guess it is the latest one if I'm not wrong. So these are the file management system, and in currently in most modern operating systems, file management system is a module which manages file information. Then we have process tables, the another structure, the another table, the most important table you can say. To manage processes, the OS needs to know details of the processes. What kind of details of the processes? Location in the memory and process attributes So memory, IO, and files, they are managed on behalf of processes. First of all, you need to understand memory, IO, and files, these are the resources and they are managed on behalf of processes. So there must be some reference to these resources directly or indirectly in the process table, because ultimately who is using these resources, file or IO or memory? If there is no process, nothing is going to happen. There is no need for any resource. These resources are utilized by program through processes. So all these resources which are managed in different data structures, like their tables, their own tables, there is always a reference from process table to all these tables, because it says that okay, this process is right now using this part of the resource. So what is physical manifestation of a process? Now this is important part. Till now we have discussed what is process, what are the elements of the process. We are going to discuss now physical manifestation of a process. Now what is manifestation? Presentation basically. Okay, in your system, what is process, right? So a process will consist of at least sufficient memory to hold the programs and the data of that process. So first of all, program and the data on which that program works, that memory, it is part of process. In addition, the execution of a program typically involves a stack that is used to keep track of procedure calls and parameter passing between procedures. Let us take simple example of C program, which is executing. You may call one function from other function. Okay, and there you require some stack because it is a procedure call. Okay, that is maintained through stack data structure. So some stack memory is required to manage this procedure calls as well as parameter passing. Finally, each process has associated with it a number of attributes that are used by the OS for process control. Typically, the collection of attributes is referred to as a process control block. We have already introduced this, right? We know what is process control block. It contains number of attributes regarding that process. This collection of program, data stack, collection of program, data stack, and attributes, that is PCB, is referred as the process image. That is the physical manifestation of a process, and it is called process image. That is called process image. So what are the elements of a process image? Now, finally, what are the elements of a process image? First of all, user data. Okay, any kind of data on which program works, the program itself, stack, and finally process control block. So these four are the elements of a process image. Are you getting up to this point? Now let us discuss a little bit about process location also. This process image is there, fine, but what is the location of this process? So it depends on memory management scheme actually, because not necessary that the whole process image, it means all these elements are always there in the main memory. It is not necessary. In modern day operating systems, we have virtual memory concepts, right? And it is not necessary that all these things are always there in the main memory. So it depends on memory management scheme. First of all, process image is maintained as a contiguous or continuous block of memory, right? Normally this block is maintained in secondary memory, normally. Okay, so the whole process image, normally you think, normally it is there in the secondary memory, except PCB is always, it is always there in the main memory. Why? We will see that. But to manage the process, a small portion must be loaded in main memory. First of all, if you want any process to execute, it must be in main memory. So at least something is there, something must be there in main memory. To execute the process, it need to be loaded in main memory or virtual memory. Okay, from secondary memory, some part needs to be loaded in main memory or at least in virtual memory. In case where process image is loaded in virtual memory, it is required for OS to know the location of each process on disk and location of process in main memory. If your process is there in virtual memory, which is extension of the main memory on hard disk or the secondary memory, now you can think that your process image, these elements, some of the part is there in secondary memory, some of the part is there in main memory. And in that case, OS needs to know that for a single process, which part is there in main memory and at which location, and which part is there in secondary memory and at which location. So location must be known to the OS for each process in main memory as well as in secondary memory. So again, once we will discuss memory management schemes, that will give you better idea how it is getting managed. So you can see that these are the process images, and every process table, I mean this process table has one entry for each process, and this process image, though it is shown here as a single block, it is not necessary that it is always a contiguous block, right? Some part may be in main memory, some part may be in secondary memory, that is virtual memory. So it can be scattered. In fact, current modern operating systems, they support paging systems. Have you heard about this term, paging system? You might have heard this term in computer architecture subject. What happens in paging system? The whole memory is divided in small chunks. They are called pages. So this is a chunk of memory. The process is nothing but process image. Process image is nothing but memory. It occupies some main memory, but that is not necessarily always continuous, right? It can be scattered in different pages. Now you think this way. If one process is scattered in main memory as well as in secondary memory, even in main memory, it is scattered across different pages. So you think about this, how many locations need to be maintained for one single process, and everything will be managed. Everything will be managed accordingly. So it is not that simple. That is why I told you that though it seems that very simple structure here, it is not simple. It is actually very complex. Are you getting up to this point? Yes, guys, are you awakened? Are you still there?
Yes, sir.
Yes. Are you feeling sleepy? See, this process is a very important concept, and once you understand it properly, then it will help you to do the programs also. Someone asked where process image is a contiguous block, right? Then how it is scattered in main? No, no, no. When I say it is contiguous block, basically when it is in the secondary memory. When it is in the secondary memory, then it is contiguous block. It is like logical memory and actual memory. Okay. For an example, when you run your program, C program, when it is stored, the C program when it is stored, okay, it is a contiguous block. Especially when it is loaded module. So again, to understand all this concept, you need to understand linking and loading and all those process, all these concepts, because logically it is a contiguous block. Logical memory means, just for understanding that, okay, my process starts with address 1 and it has address up to 100. So logically it is contiguous, but physically when it is stored in the main memory, it may be stored in different pages. So in that sense, it is scattered across the main memory. Okay, so that was about process location. Now let us discuss a little bit about PCB further. Though we have already discussed what kind of attributes are there in PCB. Further, before this lecture, in the last lecture, we discussed what kind of information can be there in PCB, what kind of attributes are stored in this PCB. We are going to discuss those things again in little detail now. Okay, what kind of process attributes are stored in PCB? So the process control block information can be grouped into 3 general categories. Again, I am repeating myself. We are discussing general OS design. Okay. Someone has sent a message. Has asked the question that paging system eliminates the need of contiguous allocation of physical memory. Correct. That is what the paging system is all about. That is the paging system. When I say contiguous block, normally when it is on the secondary memory, it is stored as a contiguous block, right? Let's say you have a very large file, which cannot be stored in one block, but normally it is stored in the contiguous blocks on hard disk. But when you get it into the main memory, at that time, first of all, not the whole file will be loaded or whole program will be loaded, right? It may be loaded in part, as well as the part which you have loaded in main memory, maybe some part is loaded in page number 1, some part may be loaded in page number 100, some part may be loaded in page number 200, likewise. I hope you are getting this. Right? So the process control block information can be grouped into 3 general categories. First, information regarding process identification. Information regarding processor state information. See, it is a processor state information. Okay. And information regarding process control information. So these are the 3 groups of the information, okay, which are stored in PCB. So what is this? What is process identification? Okay, what should be the process identification information? What do you think? What is process identification? Yes, unique identifier for each process. That is one information. But there are some other information also. So what is those information? First of all, identifier of the process. some unique ID for the each process. Then identifier of the process that created this process, that means parent process. So it also manages, every process also maintains information about its parent by maintaining its ID, So every process has its parent ID, and user identifier is also there. Okay, it also manages which user this process belongs to. So that user ID is also there. So in PCB, in process identification group, there are three information: process ID, parent process ID, and user ID. The user who has created this process or who is working on this process. So that is there. Does this make sense? Does this make sense, guys? Okay. Then comes processor state information. Now processor state is always stored in register. Simple. Okay, I think you haven't gone through this subject called microprocessor. Yes or no? Have you gone through microprocessor subject? No. So you may not be able to understand in that detail, but just think about this. Every processor has number of registers with it, and it utilizes those registers to manage the process information which is running on that processor. Okay. So this processor state information for that particular process, okay, it is managed in this group, which has three subgroups, you can say three categories of registers: user visible registers like address register or data registers. They are user visible. User visible registers means what? These are the registers which can be directly used by the programs executing in the user mode. I hope you remember user mode and kernel mode. Do you remember user mode? Yes. So when process or program is running in user mode, whichever registers can be utilized by your program while it is running in user mode, they are called user visible registers. And most of the time, these registers are nothing but they are the registers which are saving. They are data registers which save some data information. They are address registers which are working on the addresses. Okay, so typically there are from 8 to 32 of these registers, user visible registers. Although some RISC implementations have over hundreds of these registers. RISC implemented, reduce instruction set. Okay, so that is there. Then you have control and status registers like program counter, condition codes, status information, right? These are control and status registers. Program counter, basically it contains the address of the next instruction to be fetched. So that is there. Condition codes, result of the most recent arithmetic or logical operation, sign, zero, carry, equal, overflow, this kind of condition codes. So for each condition code, normally there is one register and each bit represents some of this code, right? Status information includes interrupt enabled, disabled flags, execution mode, whether this is user mode or kernel mode. So processor, how processor knows whether I am executing process in user mode or kernel mode based on the some flags which are set in some register in status information. They are also sometimes called program status word or process status word, PSW. So if you know, I mean, to understand all these details, you need to know the subject called microprocessor. But as you haven't gone through that, we are not going in much detail. But just think about number of registers which are managed. Then stack pointers are also there. We just discussed that each process image, it contains stack also, stack memory. So to manage that stack, okay, how many pointers are required to manage a stack data structure? You have gone through stack data structure, right? In any stack data structure, how many pointers are managed or maintained? Only one. That is called top pointer. We call it top of the stack, right? So each process has one or more last in first out system stacks associated with it. Now this is interesting. It is not necessary that there is always one stack. There can be multiple stacks. Mainly there are two stacks. One stack in user mode, another stack for kernel mode. Okay, and for each stack it has to manage top pointer. Okay, so that is called stack pointer. A stack is used to store parameters and calling addresses for procedures and system calls. The stack pointer points to the top of the stack. Basically, as I told you, the stack pointer basically it is pointing to the top of the stack. We call it top of the stack, right? So that was about processor state information. Three things in processor state information: user visible register, control and status registers, and stack pointers. These are the registers which are used to manage processor state information. So we have talked about two things: process identification, which contains different IDs, process ID, parent process ID, user ID. Processor state information, which contains user visible register, control and status registers, and stack pointers. And finally, we will be discussing process control information. So what is process control information? It manages information. This is the additional information needed by the OS to control and coordinate the various active processes. And what are those information? Scheduling and state information. Because if the whole discussion that we are doing here, we assume that we have a single processor. Okay, even in multiple processor also scheduling is required. At which time which process will be executing, that is called scheduling. So scheduling and state information, data structuring, IPC. IPC is inter-process communication. IPC stands for inter-process communication. Process privileges. What area of memory can be accessed by this process? What kind of files can be executed by this process? All this called process privileges. Memory management, resource ownership and utilization. So these are the different information which are managed in the PCB group called process control information. Process control information. So all these things are discussed in a little bit detail here. Process state, priority, scheduling related information, event, data structuring like queue. Normally queue is used or ring data structure can be used. So you can think like this. If you remember, these are the process states: running process, ready process, block process. And basically for each of this state, there is a queue. And this queue, it is implemented here in form of linked list. So this is how data structures are used. Inter-process communication. What is the inter-process communication? When two processes talk to each other, and how they talk to each other using some flags, signals, shared memory, messages, all those things. Okay, so to maintain all those information, it is there in process privileges. So processes are granted privileges in terms of the memory that may be accessed and that type of instructions that may be executed. Okay, in addition, privileges may apply to the use of system utilities and services. So what kind of resources can be used by this process? What kind of files can be used by this process? So all these are called process privileges and they are maintained in that process control block. Memory management related stuff. This section may include pointers to segment and or page tables that describe the virtual memory assigned to this process. So basically it comes under memory management, which we will discuss later. Resource ownership and utilization. So resources controlled by the process may be indicated, such as open file. So file is a resource, right? So a history of utilization of the processor or other resources may also be included. This information may be needed by the scheduler. So some information regarding, okay, how much processor is used by this current process, that is maintained. How much other resources and which other resources are right now occupied by this process or under this process, that ownership information is there in this process. So all these are information which are required to control that process. So again, let me repeat myself, these are general design. OS to OS, this information may vary. Some of the information are clubbed, some of the information are not there. So it all depends. But in any way, this information needs to be managed for every process in any operating system. In any operating system. And this is the image, process image. So what it contains now, you can see process image, what it contains. It contains this PCB. The upper half is PCB. Okay. Process identification, processor state information, process control information. Then you have stack, user stack. So this stack is used in the program by when it is running in the user mode. Then you have some private user space where you have all your program and data. And finally, you sometimes you have some shared address space. This is a memory which is shared by multiple processes. So this is your process image, and this is user process in virtual memory. Why virtual memory? Because some of this part may be there in main memory and some of this part may be there in secondary memory. And finally, role of the OS, role of the PCB. The most important data structure in an OS, it is the PCB, because it contains all information regarding the process. If you see this diagram, this is PCB, this three part, and it contains all information regarding the process except this stack and this address space where you have program data and all those stuff. But to manage the process, this PCB is the most important thing. Process control block requires protection, and that is very important. As PCB is very important data structure, it has to be protected by other processes so that it cannot be corrupted. A faulty routine could cause damage to the block, destroying the OS ability to manage the process. If PCB gets corrupted because of any reason, you lost your process. Any design change to the block could affect many modules of the OS. So protection is required for this process control block. Okay. So the crux of this today's lecture is this process image. That is the crux of this today's lecture. Okay. What is process image or process manifestation? So this is my process. So does this make sense? Does this make sense? Guys, are you getting it? Yes. Yes or no? Are you getting this? Do you have any question?